Okay, so how'd the hybrid topics go this past week? I saw Slack participation. It's like, yes, got participation in there. I think I got half the scattering answers, so we were talking about scattering last week and light paths. So, anyways, I wanted to kind of get into closest hit shaders and BRDFs. So, if you're in graphics for any period of time, especially when you're talking about rendering, BRDF, those four little letters are just going to get stuck in your head, and then it becomes part of just how you talk, and you're like, oh wait, nobody knows what a BRDF is. And it sounds even more mysterious when you say bidirectional reflectance distribution function, and that means you have to explain even more. So that's kind of funny. I guess we'll start out with how would you define it? So what do you think, Roshan? A BRDF, a bidirectional reflectance distribution function.
I can explain it as
what do you think we might want to do with these things? Their main utility.
Model, I think it's the model light reflection on the surface.
Yeah, that's basically, it's like how much light is reflected, that we want to know that answer. So if we have, right, we have all these lights in the room, we want to know what eventually gets to our eye. And so that's the model of how we know how much gets to our eye. All right. And in the context of the closest hit shader, we're thinking, okay, we have found the closest object to the camera, or along the series of paths that are going from the camera to the light, and we're basically saying, along all those paths, how much of it gets to our eyes. So we're going to talk about that today. Okay, so just as a matter of review, the ray tracing pipeline, we have ray generation, so we're shooting rays backwards out from the camera, and we're tracing those rays through what's called an acceleration structure. So we're going to do some kind of traversal. So we talked about different kinds, I mean, we mentioned that we haven't really defined them, but it could be voxels, so we might have like a grid. We've categorized things spatially where they're located, or octrees, quadtrees, different ways of dividing space into half. And we can basically say all the objects are on this side and all the objects are on this side, and then we can split those in half. And so instead of having to go through n objects, because it's a type of search, you can get order log n, which is a lot better than trying to search for all the objects. So we're trying to reduce, of course, log n is one of the best kinds of algorithms in terms of speed, and of course we would love to have O1, but that is very rare. Okay, so in terms of Verbigo notation, the acceleration structure is trying to take our complexity down from at least O(n), just looking through the list of objects, to O log n. So as we're going along and we're going through the different objects we're encountering in our acceleration structure, we decide let's do an intersection shader, which its whole purpose is just to handle the different kinds of objects. So we might be doing an intersection against a sphere, a ray sphere. We might be doing intersection between a triangle and an array, or soon we're going to talk about sign distance functions, which are very neat, very cool. And once we've found an intersection, then we can go ahead and call the anyhit shader. And before we define that to be, we could use it for all different kinds of purposes. But essentially, it's another check along the path of going through all objects and deciding what should we do, right? So maybe we're trying to model participating media. We talked about that last week. Marble, skin, some of these clouds, fog, any number of kinds of events. Those are one thing we could do any hit shaders for. We could use it to look into a texture map. So maybe we hit an object, but it's transparent in that region. So like a fence, right? We might model a fence as a square or a rectangle on the screen, but we might have a texture map that says these parts actually don't exist. So we use alpha testing, and so we could say, well, you hit this part of the rectangle, but it's actually transparent, so keep the ray going. So we can use that as a way of, we can have more. It's a lot faster to check against a rectangle than it is, some complicated geometry. So sometimes alpha testing is used for that kind of, I guess, assistant speed. Grass, right? That's another thing. Like if you see grass rendered or foliage rendered in computer graphics, a lot of times you'll have a texture of like a branch or a leaf or something, or leaves or blades of grass, and you'll skip half of it because it's going through, and we don't want to render that kind of geometry on the screen, so we use alpha testing to kind of help out with that. Okay, so at this point, we have gone through the acceleration structure. We have run out of objects to test against, and perhaps we have found a hit. So we ask ourselves, did we hit anything? And if we didn't, then we go ahead and call the miss shader, and we talked about, well, what do you do if you miss, right? So maybe you just have like a solid color, or maybe you want to go all out and do sky modeling. How can we come up with some kind of reflectance or light, essentially, when we don't have any objects that have been hit against? Maybe we use a cube map that kind of represents the environment. Okay, but if we did find a hit, then we call the closest hit shader. So at this point, we're going to talk about the last potential thing we want to do. At several of these stages, we may want to shoot more rays out. So the any hit shader, if this is participating media, maybe we want to shoot extra rays going in different directions. If it's a closest hit shader, we may need to fire off some more rays towards the light sources, or in random directions if we're trying to be unbiased. So that element of bias is actually a big thing in ray tracing, because in the ideal situation, if you're trying to simulate this, you would just say, well, just pick a random direction and go from there and find out what the contribution is. But if you decide that you're going to help focus the rays, because most of the rays, if you have a handful of lights, most of the rays aren't going towards the light source if you just pick randomly. So sometimes you want to help it along. And if you do that, what can happen is you can bias the ray tracer. And what that means is that you essentially, you're trying to improve image quality, but at the same time, you reduced how physically based it can be, because you said, well, we're saying this direction is important, but technically every direction is important. We have to consider every direction as a light source. We're going to talk about that today. All right, any questions so far on the ray tracing pipeline? At any point, we can imagine these as being some kind of function inside of our ray tracer. And so hopefully we'll spend a little bit of time looking at the ray tracer source code and looking at that. I believe that homework is due this coming Sunday. So this is a good time to dig in. You can use the ray tracer in there as kind of the basis. And so towards the end of the class today, we'll go ahead and look at the homework assignment, which I don't really know if I finished or not, but we'll see if it is or not. Okay, so closest hit shaders. Now we've been talking about Whitted style ray tracing, which is reflection rays, refraction rays, shadow rays. Shadow rays technically are the rays you shoot towards the light sources. So they're in a way you could call them light rays too, but one of the reasons we shoot them off is to find out if it's being blocked or not. Okay, next we get to one of our main topics, the bidirectional reflectance distribution functions. In the video, I talked about a number of them, and in terms of I mentioned them, right? I didn't actually define what they are, but we're going to take a look at some of the equations behind these. So we have Phong shading, blend Phong, Cook Torrents, GGX. These are all primarily for specular type surfaces. What did we? So, can we? What's the difference between specular and diffuse? When we use those two terms, what's the difference?
How reflective the surface is, or how much the light is absorbed or scattered.
Yeah, but we're trying to find out what the difference between the two of them are. So what makes something specular and what makes it diffuse? What's going to be the main characteristic?
Oh, light reflects off the surface.
Sure, but what are the characteristics that we're going to see?
The reflected lights. Yeah, when you saw eyes, then you can see that.
Well, they're both reflecting. It's how they're reflecting.
Specular form of color.
Yeah. So if you were to tell this to somebody on the street, you'd say, oh, yeah, I'm learning about specular and diffuse surfaces, and they're like, I don't know what you're talking about. And you say, okay, well, like the wall, that's diffuse because it's bouncing light everywhere in a room. And a mirror or, a ring, metal, cars, they're mainly specular because they just mainly reflect light. So you can look in it and you see a reflection in it. So they're not really spreading light around. Okay? So if you can almost think of it as how rough is the surface. So if it was a black and white world, specular surfaces would be perfectly flat. Light bounces, hits them, and goes off in the direction of reflectance. And if it's diffuse, you can just imagine a bunch of rough surfaces. So you never know what direction a photon comes in and it hits it. You don't know what direction it's going off. So that would be perfect. So that would be diffuse. Okay, so it's good to have in your mind because we're gonna categorize these, but we're gonna categorize them even more. Okay, because we might have instances where the model that we're using is physically based and not physically based. Okay, so and we might also say that some of these are used for realistic type shading, and some of them are used for like non-photorealistic type shading. Non-photorealistic might mean a cartoon, a technical illustration. Those are all valuable ways of viewing objects in 3D, but they don't necessarily correspond to this idea of being physically based. So we're going to really explore that today. Okay. Now, I did have this one equation on here, which is Lambert's cosine law, and we talked a little bit about this last week. Anybody? What is this n dot l going to do for us? It represents the cosine of the angle between the
normal and the light source.
Yes, and what is the normal?
Normal is the ray perpendicular to the surface.
Yeah. So.
Yeah. Plane.
Right. So this is our surface. This is the normal. We have some direction. We have some light coming in. Okay. And we have this angle here. Theta. Okay. And so we want to figure out what does that relationship kind of tell us. And sometimes it's helpful to look at different use cases, right? So just off the top of my head, I know that cosine of 0 degrees is, let's just put these out on the board here. So what's 0? Cosine of 0? 1. Cosine of 90? 0. Cosine of 45 degrees?
1/2.
What's up? About 0.707.
Yeah.
Okay, that's square root of 2. Okay, so, all right. So, what is this telling us? Cosine of 0. If we're at the cosine of 0, what is the light? Where's the light pointing? Straight on the surface. Okay, so that would be cosine of 0. Okay, and if we had cosine of 90, all right, parallel. Okay, and cosine of 45 degrees. What do we think that it's giving us? We can even graph it out. Yeah, the intensity of light on the surface. Okay, that says how much light gets reflected. Okay, now why would it make sense that when it's parallel, it's 0?
Because there's no actual intersection.
Yeah, it's almost as if the photon just skims over the top of it and keeps going. Okay, so it's not. There's no reflection at all. All right. One thing that I found is that if you have that this, it also represents the area of a parallel pipette. Okay, so if this is a unit vector, I'll make that a little shorter. If that was a unit vector, get the drawing correct. It's like that. It could be slightly wrong. I have an illustration, but the idea is that yeah. That's like this. Okay, but if you had a parallel pipette, and this is a length of 1, as it's going down, if I just draw kind of a half circle, it can kind of help me out there. As this area, so as this vector goes down, the area of this parallel pipette, you got to think 3D is going down eventually, so the area is 0. Okay, so it basically tells you how much light is going to, that light is going to, the proportion of light that will be reflected. Okay, so that's an important concept. Okay, this dot product. Now, we say that the Lambert's cosine law, we were talking about perfectly diffuse surfaces. In other words, for any incoming light, the light is bounced off evenly in every direction. Okay, we were talking about this concept here. All right, so that tells us that the entire amount of light that's reflected is, we're going to see why it's cosine 90 degrees, because it doesn't make sense necessarily why
the, the cosine kind of affects the total amount. So
we're gonna look at this, but let's get our frame of reference. Okay, so these are variables that we need to be familiar with. Okay, so we have the geometric normal. So we have n. Now there's also a corresponding physics notation that goes along with this. And does anybody remember why we have this physics notation in the computer graphics world? I've mentioned it in class a couple of times, but why might we have these physics? We have omega here, in capital Omega. Why? I have like on the left hand side, like N, V, L, those are like our nice computer science terms because we like to write things in letters because our keyboard has letters on it. But why might we have, or does anybody remember why we got these physics formulas in here?
It's to take into account the viewer in the position. If I were to look at like reflective surface from one angle versus another.
Not 100% because these are all the same things. So if I say N, I could just as well said omega G. And if I said V, I could have just as well said omega O. So the question is, where did the notation come from? Why do we have the notation? And so the main reason why we have this notation is because of the nuclear weapons research in the 1940s at Los Alamos National Labs, where they're using Monte Carlo methods to simulate what's happening with the interaction. Okay, so it's not the first time you'll ever see omega, because omega is used quite frequently when you're talking about random events. Okay, so in fact, let's just go take a look. Wikipedia is normally pretty safe, and we'll look at Monte Carlo integration. Besides the city, okay. So remember we were talking about Monte Carlo, and it's named after a famous city. But why is Monte Carlo? What is Monte Carlo famous for?
Gambling.
Gambling. Okay, rolling dice. All right. So let's go to look at Monte Carlo integration. Okay, so one good example is the estimating pi, right? So one way of estimating pi is simply just plot a bunch of random points inside of a square and then count the number that are inside the circle. And that ratio is going to give you, let's see here, the area of the square. So if you're going -1 to 1 is 4, and the area of the circle, pi times 1 squared. And so I want to say, so by comparing that ratio, you can get an estimate for pi. Okay, and so all you do is just throw random dots, and then you compare the ratio. And the more dots you throw, the better the estimate's going to be. Okay, so this is kind of where the idea comes from. But if you look over here, I'll just kind of zoom in a little bit, you'll see this omega is used. Okay, so necessarily little omega is the little W looking character in Greek. Okay, so this is kind of where the whole omega notation comes into play, and it comes from neutron transport. So let me see if there's anything in here. The neutron transport problem. And the idea was, they wanted to find out, how do you determine whether or not neutrons are going to fly through a certain object or not, right? So how thick do we have to have a lead wall or a concrete barrier? We're going to think of Chernobyl a little bit. How big does that concrete barrier have to be in order to keep the radiation down? And so the only way of really determining this, essentially, is to do random experiments. Basically. Same thing goes, I remember visiting Los Alamos National Labs and bookstore a number of years ago, and one of the big things that they do down there is they call it stockpile stewardship. And the idea there is like, well, obviously we can't test the stuff. How do you know it's going to happen, right? So they actually have computational models that say here's how these things interact, and this is one of the main reasons why the top 10 list of supercomputers, Lanel is one of those that are listed, and you can normally take a look there. Okay, but the idea here is this neutron transport problem, and so early in the 80s when they were doing computer graphics research, they were noticing that, hey, there's kind of a similarity between how they do neutron transport simulation, so figuring out how atoms are interacting with each other, and computer graphics. It's the same concept. So essentially what they did was they borrowed the more or less the same kinds of equations and just brought them to computer graphics. And so this in fact, one of the books that's out there, let me see if I can find it. It's Spellguard and we'll just go to Amazon. I think his name is Gibbard. There we go. I got this book in my office. Spanier and Gibbard. So Monte Carlo Principles and Neutron Transport Problems. This book has been around since the 50s. I think it was the 50s. 1969. That was the original publication. So, and this is actually a good book just to kind of get familiar with how and why that the Monte Carlo methods work the way they do. And then the rest of the book is if you don't know that much about physics, it's unreadable. Because, mentally you're not prepared for that. But the main the main thing behind this essentially is, how do we, if you're doing a random experiment like the estimating pi, one of the big thing you have, let's say that you do one experiment, you do 100 trials, and then you do another 100 trials, and then another 100 trials. You're going to get different answers every time. Okay, and so what you need to do is measure, well, how different is this answer from the next set of answers, from the next set of answers? And that gives you an idea of the variance. In other words, how much play is in these numbers that we're getting. And if you have very little variance and you have that gives you confidence that the number you're getting is accurate. Now, if you're seeing numbers just wildly fluctuate up and down, then you have a lot of uncertainty. Okay, but the one thing it does guarantee is that the answer is, like I said, we're using this term unbiased. In other words, it's not being swayed one way to the other. Eventually, it will converge to the right answer. If you let it run for long enough, eventually it will get there. Okay, and that's one of the cool things about. I think I mentioned the concept is, throw a bunch of random paint on the wall and eventually get the Mona Lisa out. If you had a function that mapped to the Mona Lisa, you could eventually get that result out of it. All right. So let's see here. I am looking for. Okay, so in this particular book, they really kind of highlight the Greek letters really come out when you're talking about the probability theory and all that. Okay, so if you're really interested in this, you can definitely deep dive into it. But just be aware that in the computer graphics industry, there's always the people who are really focused on, I need results now. And then there's always been the line of research that we want to make the most accurate picture as possible. Okay, so you've had these two lines going. This is why, and occasionally they dip their toes in each other's in each other's worlds. The movie guys who want the most realistic images because that is what they produce, and then you got like real-time graphics. They want the best they can, but they're limited with time and so on. So. So normally, like I said, real-time rendering, you typically see N, V, Al, and you'll see that. But even now, more than ever, I feel like if you guys watch the physically based shading, you'll notice that there's a difference in how people talk about this phenomenon. Okay, so what I really wanted to do, in terms of the frame of reference, is keep it in your mind that you're going to see two sets of variables out there, depending on the papers you're reading, and initially it can be confusing. Why are these people talking all Greek, and why are these people just talking all letters? And how do you reconcile the two? Okay, so that's what I'm trying to do here in this class. I want to reconcile the two forms. My personal preference is I like the physics ones better. Okay, and the reason I like the physics one's better is because I feel like it's making sure that I'm trying to be as correct as possible when referring to what's happening. Okay, so let's take a look at the rendering equation. All right, and the BRDF in particular. Okay, so Khajian in 1986 is talking about, hey, how do we get all this path tracing? How do we incorporate all these Monte Carlo method techniques that we've been using in physics for the longest time? How can we apply them to computer graphics? And so we have this particular equation. This particular equation is extremely important for our class. So on top of remembering the ray tracing pipeline that we're doing, you guys need to have this memorized, the rendering equation. And in fact, we're going to basically talk about it like every class for a while here until we're sick of it. But the idea here is we have a point X. That is our point on the surface that we're rendering, and we want to find out how much light is coming from point X in our direction, the output direction. Now, the reason why we don't use letters like V or E, like the viewpoint or the I, is because rather than being so focused on what we're able to see, okay, we are really focused about what's happening between surfaces. So what ends up happening is we get so caught up on I, surface, light. We get so caught up in this idea of I, surface, light, that we start to miss the point of what's actually happening. Okay? So the rendering equation is not really telling us how much light's going to get to our eye. It's just saying how much light is leaving a point. Okay? So, I mean, we of course are interested in what's happening here. Okay? But even more so,
if we have some kind of ray, we are really interested in the series I'm going to just put a light bulb here. It's a terrible light bulb, okay. Terrible dash line. We are really interested in all these events over here. This event, this event, this event, this event. We're really interested in all the ways that these light paths are traveling around, okay? So our closest hit shader doesn't, in this particular case, doesn't give us any information, all right? And this is a very realistic situation. It might not seem that way, but it is, okay? All you have to do is turn off all the lights in your house, go to one bedroom, turn the light on, and then go up to another room. You can just leave the doors open, and you'll notice that that light eventually finds its way in that other room, somehow. It's bouncing on the carpet, it's bouncing on the ceilings, it's bouncing on the walls, okay? And that light will make it, eventually, to your eye, okay? So, and that's just the reality of it. Light gets everywhere, okay? The smoother the surfaces, the easier it has a time traveling, okay? How many people watched the movie The Fifth Element? Fifth Element. You've watched it? You watched it? No. Okay, so that's a great movie. In the beginning, the whole idea behind The Fifth Element is you have this evil that's traveling to the earth, and you have this fifth element, and this kind of the movie starts out in Egypt in the early 20th century, and you have an Egyptologist is in there, and he's studying the walls, he's studying the hieroglyphics, and the spaceship's on its way coming down. But in order for him to see inside the cave, right, he has a little boy sitting out there with a mirror, some metal surface, and he's trying to reflect the light into the the tomb, into the little pyramid thing there, so he can read the hieroglyphics, and the boy's like getting sleepy, and so the joke is the professor doesn't know that the alien spaceship is on its way, and the boy's like falling asleep. And the professor's constantly reminding him, the boy's name is Aziz. He's like, Aziz, light! And so he's like, oh, okay. And he gets the light back, and then he starts falling asleep again. And then the spaceship lands, and he's like, Aziz, light! And the lights on the spaceship go on and brightly illuminate the interior. It's like, oh, that's much better. So that was the joke. It's a great scene in the movie. I really enjoy it. But the whole idea here, right, is we're wanting to see these photon paths from going on, and the rendering equation is telling us about the relationship from at this point. Okay, so here's what I want you to think about: the light leaving any direction. Okay, from a point X, and that direction is O for out. We use I for coming in, O for going out. So it's a combination of, first of all, is this direction a light source? In other words, the first one is any emission, okay, emitted light. So you can think these are your lights. This is how we represent lights in this picture. Then we take the integral over omega. Now, if you're dealing with most surfaces, this is just saying the hemisphere. In other words, if you have a solid object, we're not interested in what's happening underneath the surface, because most of the time nothing is coming through. Okay, so like these wood tables over here, there's no light coming through the surface. I mean, maybe there is a few photons they're managing to wiggle themselves through all the fibers. I think these are beaver filament, so they'll have difficult time getting through there. But the point is, we want to look at the hemisphere,
Okay? And essentially what we want to say, let's treat every incoming direction on this hemisphere, so this is like our hemisphere, as a potential source of light. And then we want to relate this, the reflection. Okay? So in 1965, there's a paper by Nicodemus, and he was basically just saying that the amount of light that's reflected, it's a differential equation, but more or less, it's whatever light, it's the ratio between the amount of light coming in versus the light going out. Okay? And you have cosine theta represents what the proportion of light that even can be reflected in the first place. We took a look at that. That's the cosine. Okay? So more or less, this reflectance over here is just, we have a function that basically states how much light coming in from the direction omega I is even capable of leaving in omega O. Okay? And if you can think of, we have lots of lights in here, but essentially this function over here, this is the recursive element of this, because now we want to say, we need to basically ask the question, well, how much light is coming in? Okay, that's what this function is all about. So this is where we shoot another ray off. So maybe we're asking the question about this point over here, and we need to find out what is the direction of light, and we'll call this omega I coming from this direction. So basically that says we're shooting a ray out in that direction. Find out how much light's coming in. Now if it was this point, that would end with the emitted light, okay? And there's no reflected light with the emitted light with the light source. So we ignore the second part, and that's kind of like your, every recursive function, essentially you have a base case where we say, okay, we're going to stop, all right? And return so it doesn't keep going forever. So this is our incoming light. This last part here, we use these angle brackets to represent the positive dot product. So we want to max, we don't want things that are less than 0, okay? In other words, because we're not concerned with light underneath the surface, we're going to ignore light coming in from the bottom. And so this basically says take the maximum of the dot product and 0. And the dot product is the cosine, so this is where the cosine is in this equation. Sometimes we'll put the cosine of theta, but in reality, when you're actually writing the algorithm for this, you need to take the absolute value, or you take the maximum between 0 and the cosine, okay? And that makes sure that you don't have any issues, because you will get issues if you don't do that. Okay, then finally we have the BRDF, and this is the function that relates the incoming light to the outgoing light. And that's the one that's kind of complicated. That one's not so easily done. It depends on what it is. So here's a figure of what this looks like, and I went ahead and put in the... Is that easily seen? Can you guys see that, or do I need to blow that up? Okay. All right. So I basically put on all these different angles here, and we can take a look at the... Let me get my images. Okay, because we really want to see what's going on here. Okay, so we mentioned all those variables on the previous slide, talking about half angle, the reflectance, the reflection angle, the transmitted light angle, and so on. All right, so I'm just going to walk over here real quick. So we have our incoming angle omega I, and you'll notice over here I have omega O going in a completely different direction. So we can kind of imagine like a flat surface. It doesn't mean it has to go in the same angle
sometimes we get used to thinking about this in two-dimensional terms. Light comes down and reflects, and we're thinking on the same plane. But in reality, the light is not just a, because if you have reflected light, right, like in this direction, you'll notice this is not anywhere on the same plane as the outgoing direction. So if you're thinking like camera and stuff, that in fact you might even have, like, when it comes to reflection, you might be interested. Well, we need to find out what the light is coming in from, along this plane. Okay, but this light over here is reflecting technically along that vector, and it's being transmitted through the surface, so if it's translucent, all right? And then your half angle is between the incoming angle and the outgoing angle. So it's just right there halfway in between, okay? And we're going to take a look a little bit, because a lot of times when you're talking about specular reflection, that's when these angles really kind of come into play, all right? But it also comes into play with certain kinds of diffuse reflection, which is why we have these other angles, phi I and phi O. So this is just a way of, we're going to see this when we're talking about the Oren-Mayer model. Okay, so this is mostly omega H. This one. You're talking about this one over here?
Yeah.
Yeah, omega H for the half angle.
It's a half angle. Okay, so let's go over here. So just as a matter of review, we talked last week about Paul Heckbert's notation, where we used the term E for I, L for the light vector, S is a specular interface, D is a diffuse interface, and this is just a way of talking about different kinds of light paths. All right, so I'm not going to talk too much about this today, but I just wanted to put this in as a reference of how we talk about single paths or several paths. All right, so this one over here might be an example of an LSD plus E type light path. Okay, so we have this idea of how much light is reflected. Okay, and so there's a few laws that it has to obey. The first one is conservation of energy. It means you cannot reflect more light than comes in. And the way to check this, so it's almost like a checklist. You can apply this checklist to the different BRDF models to determine whether or not it is actually physically based. Because some of them were conceived to be for generating realistic images, but not all of them are actually technically physically based, even though they might look pretty good. So the first one is, if you were to integrate your BRDF over the entire hemisphere, then it should make sense that you should never reflect more light than it came in. So this should be less than or equal to 1. Secondly, you have Helmholtz reciprocity, which basically means, here's a good way of thinking about it. If you have light coming in and light going out, it doesn't matter if you just swap the direction that you did, that it came in, right? So, in other words, if you were having light reflect that way, it should reflect exactly the same way. And think about how weird it would be if you stood on or looked in a mirror and from one angle it reflected light that way, and then you stood at the other side and then it kind of bounced back. That would kind of be a strange mirror. It didn't behave like that. So Helmholtz reciprocity means if you just swap the angle, the function should be the same, which makes sense. Okay? Or maybe another concept to think, it would almost be like saying if you're shining blue light here and you get red light out,
or some other kind of strange phenomenon. That just doesn't have it. The stuff gets preserved. All right, so you have reciprocity. Secondly, you have positivity. This means that you are going to reflect light. Okay, it's not less than zero. If you could think about it, what would if the reflectance function was less than zero, how would that even work? It's almost like a vacuum, right? It's like sucking light out of the system, you know. So you can't destroy light, in other words. So I think positivity and conservation of energy kind of go hand in hand, right? You cannot create energy, you can't destroy energy. And so positivity means that you basically cannot destroy energy, all right? And then lastly, we have conservation of visible projected area. Now this is a relatively new one because a lot of times this is not really applicable when you're talking about perfectly flat, smooth surfaces, okay? It's always the cosine. It doesn't matter what. But what this is getting into is the idea is that we can have microfacets, all right? And if you have some kind of surface, I'm just going to draw this out here. So up until now, we've been talking about like perfectly smooth surfaces, but let's just imagine, and for all intents and purposes, what we're doing is we're trying to imagine this at a much smaller scale than the surfaces we see. There's a reason why we have the geometric normal, which is more or less how flat the surface is, and then there's what's happening at the microscopic level. Okay, so you might have a flat surface that we're modeling, but we might be modeling that it has some kind of surface profile to it. Okay, and there's different ways of doing it. You could just simulate, well, what is it actually like, right? So, for example, if you're doing cloth rendering, you would need to simulate the behavior of the weave on the fabric. Okay, now if you look at my clothes, right, the surface is flat, okay, but there's some micro scale geometry going on, which corresponds to why fabric looks the way it does. Okay, so we normally have we have this concept of omega m, which basically stands for like the microfacet, what direction it's pointing in. Okay, so the microfacet could be different, could be pointing in completely different directions. So I'm just going to use this for. And then you have the normal, the geometric normal. Okay. So what this bottom equation is saying is that if you were to project, and I'm going to shine the light like this. Okay. This is the direction that the light is coming in. Okay. Essentially, this, let's say this represents like an even area. This over here has to be equal to the cosine of this surface. Okay, because technically this has more area. Okay, but we're interested in the projected area. Okay, and this function g1 is called, it's like the masking function. In other words, like this area is masked. So you have masking and shadowing going on. All right, so that's happening. And so basically, if you were to take your masking function and integrate it over the entire hemisphere, then you should get the same area as if you had pretended that there was no microgeometry at all. Okay, and so that's basically saying conservation of visible projected area. That one's kind of a new one that really hasn't been in computer graphics around for, I guess, more than a few years. People are really starting to think about even the reflectance functions. Can you make sure that they're actually
physically based. So let's talk about diffuse BRDFs, because I feel like these are the more simpler ones to understand. So when it comes to Lambertian, we have that it's actually pretty easy for us to do these tests, right? So the idea behind Lambertian is that it's constant. So it's rho over pi. Rho over pi.
And I wanted to explain this just a bit.
So essentially, if you were going to calculate the rendering equation on this one,
a lot of times the outgoing light essentially equals rho over pi times the incoming light, whatever the intensity is, times cosine
theta I, which is the incoming. So that's the dot product. Now, rho happens to represent the absorption of the material. Okay? The best way to think about this, that's the color. Okay? So if it's reflecting red, then we would expect rho to be the color red because there's no reflection of green and blue. So we're just thinking RGB here. All right? And light, the incoming light, that's just the intensity of the light, so whatever the color of the light is. And then cosine theta I just says, here's how much of that light can be reflected. And this is one of those simple looking BRDF CRR. It basically just says that our surface behaves like this. Now, I wanted to explain where the pi comes from. So, the pi happens to come from the fact that we have to take into account the area of the hemisphere. All right? So, just for a way of reference, area of a sphere. Okay, so area of a sphere is 4 pi r squared. So that would make the area of a hemisphere what? What's the area of a hemisphere? 2 pi r squared. Okay, and if the radius was 1, it's 2 pi. All right, so the reason we have this pi is because it represents that area. Now, there's a reason why it's pi and not 2 pi. And let's I think I'm gonna have to look up I wanted to show you the math behind this, because it's easy to forget why we have pi or 2 pi. Okay. You can tell I spent a lot of time thinking about this. Okay. Okay, so here's how we do that integration for the hemisphere. Howdy, can I help you?
Hello. I'm just really
Oh, okay, for the next slide. Okay, yeah, feel free to take a seat. Okay, so we want to let me zoom this up so we can actually see it. there's a little trick that you have to do, okay, and that's if you're the d theta of sine squared theta equals 2 cosine theta of sine theta. So we're going to do the hemisphere, because what we want to do is we want to take this integral over omega, and we're trying to actually, well, how do you actually integrate that? Okay, so we integrate, and this should make sense. We're just doing double integration. This is something you might do in calculus too. Okay, so we're integrating theta over 0 to 2 pi. Actually, we're integrating phi from 0 to 2 pi, and then we're integrating theta from 0 to pi over 2. Okay, so we're, in other words, going from the top all the way around. So when we do this integration, we are left with sine squared theta from 0 to pi over 2 times the integral of d phi. Okay, so that's going to be pretty easy. So we end up getting sine squared of pi over 2 minus sine squared of 0. So that's 1. And we 2 pi minus 0. So that gives us 2 pi. Okay, fair enough. That's what we were thinking it was. Now, we have to normalize the integral. So, in other words, if we want our f sub r to come out to a value of 1 when we're all finished with it, we need to figure out, well, what do we need to multiply against our this hemisphere in order to get 1, okay? So it's 1 over 2 pi. 1 over 2 pi. So that's the normalized area of a hemisphere. Now, here's the reason why we have 1 over pi. Okay? It's because when we multiply 1 over 2 pi times this integral, you'll notice the 2. That's where the 2 disappears. And now we're left with this integral. Okay? This is the trick behind the rendering equation, that we have this 1 over pi constant in front of it. All right? And you'll notice that the sine theta, d theta, that part will we'll basically eliminate that, because we're going to go back to just saying, well, this is the integral over the hemisphere. All right. So, if we have, oops, too much. Okay. So we have our Lambertian as rho over pi. So we're going to actually integrate this. Okay. So we move our, we're going to factor out our 1/2 again, and our f over r. So we already know what this is going to be. That's going to end up being 2 pi. And we know that f sub r is rho over pi. And then so the 1/2 times 2 goes away again. So we're left with f sub r times the incoming light times pi. And then when we have pi over 2 times our incoming light times pi will cancel out. And so we're basically just saying that, remember, rho is absorption. So we're saying that the outgoing light equals whatever that absorption is times the incoming light. All right? Does that make sense? Okay. I was really bothered by this. Hand waving. Where in the world did they get rho over pi from? And where is the 2 pi coming from? Because we know that if you integrate the hemisphere, it's 2 pi. And now we're saying that this is rho over pi. And I wanted to find out, where's the hand waving? What is the trick? This took me a long time to sit down and figure out that the way that they got this function to be the way it is because of the way that the normalization has to do with the normalization of the integral. Otherwise, you completely ruin the conservation of energy. Okay, so Okay, so sometimes this can be a little tricky to remember. It's almost like asking, everybody probably can recite the quadratic equation, right? But then if I asked you, okay, go ahead and derive it for me, everybody said, I'm quitting your class now. Okay. So this was kind of what I had like perceived. I'd seen this, and I was like, how do they come up with this? How did this rho over pi come up with? And I'm saying this because, you know, we just happened to mention it. It's like, yeah, the Lambertian one is just rho over pi, and then you're just going to multiply rho over pi times your incoming light times your cosine theta for your angle, and then you're going to call it good. Okay? And so I wasn't exactly satisfied with that, so I really like sat down and I was like, I'm going to work this out and find out why is it that this is how it is. Because I couldn't figure out for the life of me how they got, it wasn't 2 pi because of the radius of the area of the hemisphere. Okay, so now you know it has to do with the normalization of the hemisphere, so you can kind of, you have that factor of 1/2. It's kind of factors itself out. Okie doke. So the next thing is the Aurier model. So if you've ever looked at in fact, we've seen the Lambertian one in practice. That's the one that is currently on the current demo. So if I think I have, go back here. So just looking at the ray tracer, right? This is essentially Lambertian reflection. Okay, now you'll notice that it doesn't exactly make sense, because if you look at the moon doesn't reflect light. There's lots of things that don't reflect light like this. Okay, so if you ever look at the moon, you're like, one half's dark, the other one's practically, you know, half lit. So where does that come in? So I thought it might be interesting maybe to modify the ray tracer just a hair to see what happens if we put the Aurier model in. Okay, so but before we do that, okay, so they actually use the model to come up with these numbers. All right, and so the idea is that we would plug in the sigma squared, which happens to represent what's the variation of the microfacets on the surface doing. Okay, because they're trying to model dust. Aurier kind of gives, you know, what happens if the surface is dusty. Okay, but we haven't 100% finished talking about speculative BRDFs, although I think we might talk more about these next week, because I don't want to skim over this too fast. But I think it is important to note that this is the model essentially for specular BRDFs. So you have the distribution of microfacets. In other words, how many what percentage of the microfacets are pointing in this direction? What percentage is pointing in this direction? That's what that function tells you. And that one's not too complicated. Then you have the Fresnel. So what does the reflectance do to the Fresnel? And then you have G2 over here, which is we mentioned G1 earlier, but G2, we'll see in the next slide real quick, has to do with, that's the masking shadowing function. And you can't just consider masking and shadowing from the incoming light, you have to also consider the outgoing light as well. They're both those angles, you have to consider it from both sides. So they call it G2 because we're using both of them. And I'll tell the interesting story about the Smith function. There's a one called the Beckman distribution. This was back in the 60s. I think the 60s. So there's a guy, Beckman, he wrote an article about scattering from, Gaussian type scattering. And then there's another guy, Smith, to call him out. It's like, no, you have an error in the way you're thinking about it. And there's like a whole new function that he essentially derived. Okay. Okay, so just real quick before we leave the slide, this is the distribution. So a lot of times, like Phong shading, you more or less think, okay, we're going to raise the dot product between the geometric normal and the reflection angle, not the half angle, but the reflection angle to some kind of power. The higher you raise that exponent, the shinier the surface looks. That's not physically based. A better one is called the Blinn-Phong model. You do the same idea, except you use the half angle instead. And I don't want to skim over that. So we'll talk about that more next week. And then there's another one called the GGX function, which models the surface in a different way. But this masking shadowing function is, I said G2, so if this was G1, it would be 1 over 1 plus this lambda function. And so this lambda function for GGX is this huge equation over here. And I'd rather talk about that later. GGX looks pretty nice. Okay, then there's the Fresnel equations, and I don't want to skip over this too much either, but there's a approximation that looks pretty good, and if you want to do metal, you can calculate the Fresnel at 0 degrees. That's what this F0 is talking about. Okay, and then for the hybrid topics, so on Thursday, I'm gonna do a video on global illumination and one on spherical harmonics. We'll see if I get to the spherical harmonics one, but we'll be trying to talk about two of those concepts there. Okay, so let's bring this up. So we're going to talk about the shiny stuff next week. We're going to talk about all the dull stuff today. Okay, bad joke. Okay, so we're going to try and implement this real quick. We have 13 minutes. So I'm going to go to my my sample code here, and I'm going to copy example 7. Okay. Something's slowing my computer down. This is probably it. Okay. All right. So over here, change my thing to 9. Change my HTML file. Get rid of my helpful HTML5 functions. Modifying code earlier today, and I put this in a different file, so it's not. I should probably get rid of that stuff too. Oh, I know what I did. We need 6. Okay, so let's save this. And I should have done this before class, but you guys can see behind the scenes how I put all this stuff together. Okay. All right. So let me go back to example 9. Actually, close all. Change the shader that I load up.
and find out why that's not compiling. So I found that Edge is pretty good for, I like to make sure that everything works in Edge, but I find that Chrome still has a slightly better debugger. So I'm going to use Chrome for debugging purposes. Okay, so that's working. Good deal. All right. So let's go down here. You guys can look at the source code for this to, trace through, like run, just trace through the flow of the program, and you'll see more or less how I use it to implement that ray tracing pipeline. So shaders, closest hit shader. Okay, so this is the one you'll see over here that I'm multiplying the diffuse color, so that represents the row. You'll notice I'm not dividing by pi though, so maybe that's something I could do, right? To be more accurate. Let's use 3.14159. It's probably plenty good. And see what happens if I reload. It got darker. All right, that makes sense. Okay, so now I need to come up with a way of making it brighter. So just going to declare constant. Can't do that. It's one of those things in GLSL, 10 is not the same as 10.0 because the integer math and the floating point math, it's very strict about that. Okay. All right, so this kind of clues us in a little bit to why the moon kind of looks so intense, right? When we have a sharp edge. So just using the Lambertian, the Lambertian equation, you'll see that we still have a fairly bright fall off, but it's not smooth. Okay, and so if you look at the moon, more or less, it still doesn't 100% look like that. Let me turn this one white. Actually, we'll turn it to gray 67. We'll pretend like we're actually trying to simulate the moon. Okay, because I think the grays really kind of bring it out. So if we turn this up, so it's 100.0. Okay, so you still kind of get this flat. Like the more I guess you drive up the intensity with the sun ought to be, then you kind of get that layer. But let's go down here, because a lot of services, like the lights inside of this room, for example, are not that bright. So we're going to go back to 10, but now we're going to go ahead and implement this this ordinator function. Okay, so there's a few things we need to calculate. So we have A and B. So A equals 1.0 minus 0.45. We're just going to say that this S equals the s squared value. So that's s over s plus 0.33. Yeah. And b equals 45. That's what. B equals s over, I want to say it's 0.09. Yeah. Okay. This leads us to another one of our, you're going to find like the ordinator model, and then you're like, well, how do you calculate sine alpha and tangent beta? And how do you come up with what the heck they even are? Okay, because it comes, we have this theta I, theta O, and we have this phi I, phi O, which I showed you in the graph that represents where the relationship is between the outgoing vectors and the incoming vectors are. Okay, so at some point I was able to kind of work on this equation a little bit and figure out what are these calculations. Okay, and what it's kind of interesting because it's like a determinant going on. That's if you take that cosine, there's a determinant calculation going on behind the scenes that if you kind of work it all out, you can kind of get rid of, and this is how you, in computer graphics, you're trying to get rid of things that you don't know and write them in terms of things that you do know. So for example, if you ever want to find out what the sine of an angle is, but you only have the cosine, how would you do that? Yeah, you just say, okay, the sine equals the square root of 1 minus cosine squared theta. Now you got the sine. You didn't have to go about, because the sine's kind of, the sine is kind of related to the cross product. Okay, so you have dot products related to cosine, and you have cross products related to the sine function. If you look at a cross product, it looks an awful lot like a determinant. Okay, so I'm going to do some hand waving today and try and find some ordinator code real quick. I'm just looking for a shader from a while ago. What did I just do? Okay. Working, shaders. Okay. Okay, I'm going to copy this. Whoa. I need to pass in a roughness value. Cool. Float S.
This stuff normally requires some anticipation of like values that you're going to need. All right. Save. Okay, so we should be able to calculate the ordinary value now. We just need to pass an n, and v is L this is the direction the ray is traveling. Okay. We got something half working. Okay. I'm going to call this half of the success. But if you notice, maybe it's possible I'm not using this 100% correct, but the idea here, let me go over here, so we're returning, oh, we still need to calculate, and we can get rid of this, the division by pi. Okay, and if we have s is equal to 0, then we will technically get the original model back. All right, which is what we have. And if we set s equal to 1, then we should have a, what I like to call a dustier surface. So let's see here. It's kind of hard to tell. Well, I mean, it looks like it's working. So if we increase, basically, if we increase the how randomly, I guess the intensity, right? So that sigma is basically says how rough is our surface. I'm trying to see if I can tell the difference. I think technically we're out of time, but this is something we'll take a look at some more on next Tuesday, and hopefully I'll try to get a page up where all these examples have been pushed to and stuff. But this is just to kind of show you a little bit of taste. The stuff cannot be done in just 10 minutes. I hope that's a takeaway from that. You can't just do this stuff in 10 minutes and poof. But it's almost close to that if you've kind of done the work out and you understand what's happening over here. So at some point in time, I'm going to kind of migrate some of these equations over to the to our source code base so that we can actually use all this stuff. So all right. Well, I think that's all I have for today.
And I think that's it. All right, so I'm going to turn off the streaming, and then we'll get ready for